Thank you. Thank you. Well, let me start by thanking the organizers for the invitation. It's such a nice opportunity to be here. Really great. Yeah, it's my first time actually in this institute. Well, and I wanted to use this opportunity to tell you a story about light mediated interactions. It's perfect after that my talk is after Julian. Um, so what the story that I'm going to tell you about is a work that have been done in the last few years that makes me believe that atoms interacting via long-range interactions in cavities offer really great opportunities for quantum simulation and sensing. And hopefully I can convince you after this talk. Before starting, I wanted to acknowledge my collaborators. The work I have been doing on cavity QED has been in collaboration with James Tonso at GILA, and of course his group of very nice postdocs and grad students. And I have also the pleasure to have fantastic students that even go to James' office, James' lab, and they model the experiment together with experimentalists. It has been very fun. All right, so just to share my scientific vision that I think is shared by all of us here. So basically, we wanted to harness quantum complexity and we wanted to understand the behavior of many body quantum systems and use these systems for various relevant applications from quantum simulation, information, and quantum metrology. And well, we know that ultracold atoms, molecules, and ions are really open, very important opportunities over this direction because they're allowing us to bridge the very complicated gap between the behavior of few body systems that we know how to model and understand to the complex behavior but exciting behavior of many body systems. And well, I mean, we know that these systems have very important opportunities towards these tasks. They allow to have Hamiltonians that have pristine parameters and very well understood microscopics. We can tune the parameters of the Hamiltonian even on real time and can access quantum dynamics without needing ultra-fast probes as you need in solid-state materials, for example. And well, I mean, with this, I mean, the goal is try to use this control for different exciting applications ranging from quantum simulation, quantum sensors that are beyond what we can do with classical systems, trying to shed light into very complicated open questions about the universe, and of course, the dream of building quantum computers. And well, we know that in fact, these systems are really great and can help us towards this task. But what I want to start reviewing now is that even though they are very powerful, we are facing very important challenges that we need to overcome. And for example, one very important challenge, if you are going to pursue the need of quantum to build a quantum simulator, cooling has been really hard. And the reason is that because if we wanted to emulate the behavior of condensed matter systems, which the phenomena happens at Kelvin type temperature, the discrepancy in masses and energy and lattice spacing imposes the need of reaching temperatures even below nanokelvin to see similar type of phenomena. So this is very challenging, and of course we have done a lot of progress towards cooling our systems, but the truth is that we're still really hot compared to what is needed. And the question is, what could be the solutions? One way to go is to notice that, well, in fact, when we were starting to control the motion degrees of freedom of our systems and have access to Bose and Fermi gases, and even later trying to manipulate the motion of the system by trapping them in optical lattice and open a path for connections to solid-state crystals, emulating the electrons in ion lattice, in the ion cores, building the Bose and Fermi Hobart models. Then one of the key issues is that in order to see, for example, magnetism in these systems, the only way that we can do it is through motion, because the particles have contact interactions, and the only way that one is spinning one latticite feel the other is that to jump in the other latticite and come back. So spin and motion are intertwined, and this makes seeing the physics that we want very complicated. But instead, if we have systems where the spin and the motion are decoupled, and still we can have spin interactions, even in frozen gases, then it's very helpful because, well, we have our frozen gases, and moreover, we know that the optical pumping and different things, we are able to cool the spin degrees of freedom, even the motion is still hot. But then if we are able to explore the spin degrees of freedom, then it can open in the future a path to understand the motion. And in fact, systems where we can reach interactions even at a distance where the particles are frozen are many systems that are becoming very developed in different experimental groups like polar molecules, magnetic atoms, Ripper atoms, trap ions, and atoms in optical cavities all offer a possibility to explore such type of physics. And in the future, as I said, maybe as we control the spin degrees of freedom, we open a path to also start to control the motion and have some leverage of the quantum statistics. The second big challenge that we are facing is the entanglement generation. Because, of course, we are competing with the coherence of other rates in order to generate entanglement. And there are fundamental bounds that we have to overcome when we are trying to generate entanglement with short-range interactions. These are, I always represented atoms interacting by contact interactions, like our hockey players, that they really need to be in contact in order to transmit information, and they are really subject to very strict Lieb-Robinson bounds in order to transfer information. So it's kind of a domino that has to go one step at a time. But on the other hand, if we have the possibility to have all-to-all interactions, then we have more like hockey players where the ball can go at very fast distance. And in fact, if we have systems that interact and have connectivity with every particle in the array, then we are not suffering with these bounds, and we can reach the entanglement generation much faster. And in fact, we have systems in optical cavities or trap ions that they are ultimate systems where really the information can be transmitted at infinite range. So all the atoms talk to each other. So, and in fact, I mean, in order to emphasize the relevance of these systems, if you look at the table of the entanglement generated over the decades in atomic systems, including atoms, ions, and many different type of settings, you can see that still the record levels of entanglement is reached by systems in optical cavities. This is experiments in Cavities and James Thomson that reach really metrological gain of the order of 100. So although it's very exciting, I just citing many platforms are starting, of course, to start reaching conditions where this can be overcome, but still we see that these platforms are the ones that have the record levels of entanglement. And well, the vertical axis is the metrological gain, and I'm talking about entanglement, how can be used for metrology. So this is a spin squeezing in many degrees, and we characterize this in dB. So this is about 10 dB, 20 dB. I mean, these states are reaching 28 to 20 dB. So it's how much you can outperform classical systems. That's the metric. I will explain a little bit more on that. So yeah, but I mean, some of the experiments, for example, in trap ions have also prepared some of the cut states. So here I'm mostly quantifying entanglement that is useful for metrology. And the last challenge that we have is the tension between control and scalability. Because, of course, what we wanted to do is we wanted to control as many particles as we can, but this goes at the trade-off that we cannot control them the best we can, yes? And what could be a solution? Well, it's hard, but perhaps one direction that we should start thinking about is the idea that maybe instead of using qubits, we go to qubits. Then we open the possibility to have less particles, but similar number of accessible levels in our system. And the fact is that atoms are intrinsically multi-level. So many times what we do is just isolate a set of levels in the atoms in order to operate with them. but maybe that's not the way we should do. For example, in the case of strontium, that is one of our favorite atoms at GILA, that is one of the key atoms for atomic clocks. This atom has two very long-lived levels, each one with 10 different states. That opens a path for many opportunities on quantum simulation and metrology. But of course, it's not easy to control so many levels. So it's always a balance between what they offer and what we can control. And finally, the last challenge that we have, of course, is how we are going to control the dissipation. We know that, of course, we wanted to keep the system as coherent as we want, and the environment very quickly killed the dissipations that we have. So one possibility, there are many possibilities. We wanted to build the coherence-free subspace, detect and correct errors, like error correction is becoming one of the very important directions. But alternative, one can also try to look at ways that we can, there has been also different talks in this workshop on how we can engineer the environment and trying to land in a system that we want. But alternative, what we can do is that we can actually use the entanglement itself via measurements to land in the state that we want. And what I'm bringing this up is that, for example, in these cavity systems that have reached the record levels of spin squeezing, the entanglement was done by weak measurements. So measurements that don't destroy the information, they extract some level of information, but they still keep the system entangled. So what I was bringing all these different challenges is that I want to tell you one possible solution that we can offer towards them using cavity QED systems. So, for example, the first challenge, trying to reduce the temperature for quantum simulation, maybe what we can do is try to build synthetic materials where this can be handled in an easier way. The challenge too is entanglement generation, and these all-to-all interactions allow, of course, for faster entanglement generation, but we wanted to push the limit at which entanglement can propagate. So this can be even by engineering systems where the entanglement propagate exponentially with time, or build up exponentially with time, or alternative, we can build systems where we only have two-body interactions, but instead we have multi-body interactions. And respect to the multi-level systems, maybe we can use these multi-level atoms actually to prevent decay and create states that are completely dark to the coherence. And respect to the challenge of dissipation, in fact, maybe we can try to control the dissipations in cavity systems and land to states that entanglement through the dissipation that they have. So I don't think I will have time to tell you a story about that, but I'm happy to discuss. But I hope I can give a little bit of some hints of what we are doing towards these three directions. Okay, and well, this has been done in collaboration with James' group. So let me first starting by briefly introducing the system that we are working on. So we are working in a new regime of cavity QED in the sense that we are using ultra long-lived atoms. So there are atoms that have a very long optical state that can live for a very long time. For example, the clock state can live for 100 seconds, and we work in another state that is the excited state, the trippy one, that it lives 22 microseconds, but it's still much more longer than any optical allowed dipole transition. So when we place these atoms in an optical cavity, let me start by just considering just two levels. Then the Hamiltonian is dictated by the standard Tavis-Cumming Hamiltonian, that it says where delta C is the detuning between the cavity and the atomic system. And we have an exchange between the photons between the atoms and the exchange of photons between the atoms in the array. That is all-to-all, that means an atom absorb and emit independent where they are in the array. And of course, well, the system is not completely closed because photons can leak out the cavity as array kappa that introduces dissipation in the system. So now what we wanted to do is operate in a regime where we, at the moment, adiabatically eliminate the photons. We don't want to deal directly with them. So we work either at large detuning or large cavity decay. compared to all the parameters in the system. And when we do that, what happens is that the photons become completely slave to the atoms. And therefore, we have a one-to-one relationship between of them. So A, the field operator of the photons, is becoming proportional to S minus, that is the dipole moment of the atoms, the collective dipole moment. So now in the regime where the cavity detuning is larger compared to any other scale, then the photons cannot escape, they cannot escape out of the cavity, they remain there, and therefore an atom in the excited state emits a photon which is absorbed by the other atom, and this engineers virtual exchange interactions between the atoms, forming what we call an exchange interactions, but in this case it's all-to-all. So every atom in the array exchange, and this all-to-all S plus S minus can be also written as S squared minus SC squared. These are collective operators, and there are many groups in the world trying to deal with this very long-range type of exchange interactions. So these type of interactions are useful because of many reasons. One is that you see here S squared Hamiltonian is a ferromagnetic Hamiltonian that introduces a big energy gap, and this big energy gap can introduce diminish the susceptibility of the system to inhomogeneity because of local noise. So there is a lot of possibilities to explore this as prolong the coherence of the system. And a physical picture of that, if you have a bunch of non-interacting atoms, they will dephase very quickly. But on the other hand, if they are interacting via these gap protections, they remain circulating around each other. This is gap protection. And I'm going to tell you a story how we are going to use it in a bit. We have also the possibility to use these collective interactions, for example, to look at what is called dynamical phase transitions. One of them, for example, is the Lipkin-Neshko-Grilk model that have a dynamical phase transition that we can probe in the cavity. Or, and this is going to be the main topic of today, we can try to use these systems to emulate dynamical phases, for example, of BCS superconductors or BCS superfluids. And well, let me tell you a little bit more how we are doing that. So, of course, when we talk about superconductors, we know that these are very, very useful and very interesting systems that can have a broad of different applications. And we understand them, at least the conventional superconductors, very well. We know that the electrons form Cooper pairs because they feel attractions through the phonons distortion in the crystal. And of course, they are very well described by BCS Hamiltonian that I'm going to show that was awarded the Nobel Prize a few years ago. So what is the idea? So if we have non-interacting fermions, well, we know that because of the Fermi statistics at low temperatures, we form a Fermi sea where all the levels are occupied below the Fermi momentum. And we have, yes, the kinetic energy, here's the chemical potential. And the idea is that when we have attractions between the electrons because of the phonon deformation, then the relevant term of the Hamiltonian is the term when you destroy two fermions in opposite momentum and spin, and you create the corresponding another pair. And this term favors pairing from the formation of Cooper pairs. And in the form, this is the Hamiltonian for the case of S-wave attractive interactions. So basically, in order to minimize the energy, what the state wants to create is a coherent superpositions between Cooper pairs and empty sites, and that is what rules the behavior of a superconductor. These coherences between these two is what gives rise to a minimization of the energy in the BCS model. And there is a way to characterize at the mean field level this type of coherence by what we call the BCS order parameter, that is the expectation value of CC. Okay. Yes, these interactions are in principle all-to-all because it's in momentum states. There is going to be a cutoff, but this is the phonons. This is the phonons. I'm just trying to emulate how this emerge. So the phonons introduces attraction between the electrons, and I'm just looking at the electrons here. I already eliminate the phonons. There is a lattice, but in momentum space, the interactions are all-to-all. Is any contact interactions when you write it in momentum, they become all to all. Yes. Well, the interactions are still, I mean, the BCS model can have a frequency cutoff here. But with the standard BCS model, you write it in momentum space, and you write. It's a very special model, but it's the BCS model. Yes, but that's what that's what it was in the original BCS paper, this BCS. Yes, it's the Richardson model of BCS. Yes, exactly. It's the Richardson model. And I think what we are doing is that we are only considering Cooper pairs and empty sites, and that's what rules the behavior. So, and using this model, for example, there has been predictions by condensed matter theories of what are the different dynamical phases that can emerge when you quench the order parameter from one value to another. There are, because this model becomes integrable, exactly the Richardson-Gaudin model, then you have a lot, they admit an exact solution, and they propose that they have three dynamical phases that rules the behavior of superconductors. They call phase one, where the order parameter decay. First two, where the order parameter just keep stable and they have just small weak oscillations. And they call phase three, where the order parameter keeps oscillating permanently, and kind of this is the analog of time crystal. So in condensed matter systems, there has been only indirect evidence of this phase two with some evidence of the Higgs oscillations, but they have not seen these different phases in the system. Now, with respect to the connection between BCS superconductors and superfluids, for example, here at Gila, David Jean, one of the pioneer experimentalists that were able to cool down fermionic gases, and you can bring them very close to a Feshbach resonance, where the interactions are become very strong, so a very aggressive Hopke graders, and then you can see enter the regime of hydrodynamic behavior, some connections with high TC, quangular plasma. Well, this is in principle was to be the exciting part of the phase diagram to investigate by tuning the magnetic field, but also there is some indications that there could be BCS-BEC transition in the quark-gluon plasma when you have the hadrons that form the analog of the molecules and the color superfluid that is the analogs of the BCS pairs. In the atoms, however, when you directly try to implement these models in atoms, there are a lot of cooling problems still, especially because if you have a collision of the atom with a background gas and remove this electron, this atom from the lowest, for the bottom of the trap, then it gives rise to significant cooling. And therefore, there are various experiments that are trying to use cooling in order to cryogenic conditions in order to remove this process. And quenching the magnetic field is also not so easy. And also there are a lot of losses close to the Feshbach resonance. However, for example, we were looking at this problem a few years ago. We thought that maybe by operating instead of the strongly interacting regime, if we operate in the weakly interacting regime, this was an experiment done with Joseph Typacine, you were able to more easily simulate connections with BCS superconductivity. I'm going to explain a little bit what is that. But it was using the cavity where we were able to see the dynamic, all the phase transition 1, 2, 3 in the same system. So let me explain a little bit more. So the idea is that in order to emulate the BCS model, we have the kinetic energy and you have the interactions. And if we use what is called the Anderson pseudo-spin mapping, that said, well, at ultra-cold temperature, you only can have Cooper pairs on empty sites. Also, all the states that have a single fermion are high energy. So then we can reduce this model just to a spin system, spin up the Cooper pair, spin down the empty site. And therefore, instead of writing this term in terms of spin or fermionic operators, we can rewrite it in terms of spin operators being S minus, for example, a term that destroyed a Cooper pair, and C is a measurement of the number of particles in the system. So if we do this mapping, then this Hamiltonian, you can see that it becomes S plus S minus, collective S plus S minus. And we can also have another parameter just the expectation value of S minus, the collective S minus of the system. So with that, then we propose that we could, in fact, emulate the BCS model in the cavity because, well, the S plus S minus are the exchange interactions that I discussed before. And now, if we wanted to engineer the single particle term, this is easy to engineer via star shifts, but we also need to include some form of the Fermi statistics. We know that, for example, if you look at the ground state in this spin, Anderson said the spin mapping, all the spins are going to be pointing up, or that means occupy below a Fermi level, then there is some type of canting, and then all the states are down. So we wanted to emulate this type of conditions in the experiment, and for that, what we did is just to add a star shift to only one part of the cloud, and therefore it creates a situation where you can see the particles that are on these regions, you want to have the spins pointing down, and the particles in the other region, I mean, when you change the sign of the magnetic field, you can engineer an effective two big spin system that can have similar behavior as this. And moreover, in order to read the superconducting order parameter, we just need to look at the photons leaking out of the cavity, because in this case, this is exactly one-to-one mapping. So by doing that, we were able to do quenches of the superconductor, because we were able to start, for example, apply a pi-half pulse and prepare all the atoms pointing along the x direction. That is the situation of a very strongly interacting system, and quench the dynamics to other, this is the chi n is the interaction strength. So we can change the system and to different values of the interaction strength by controlling the number of atoms, or also we can tune the star shift that is introducing the different inhomogeneities between the levels. And we can see that, well, of course, in the ideal system, we are going to do in the phase 2 perfect phase. But in the experiment, nevertheless, when we introduce some inhomogeneities, some addition and things, we still see very clear a phase transition between phase 1, where everything decays very quickly, or phase 2, where the system starts to remain at a finite value. And we plot, for example, the value of the superconducting order parameter as a given time. We can see a clear transition that agrees with the theory. Solid lines are theory, dots are the experimental points. And on the context of coherence, we can see that we can enhance the lifetime of the coherence of the system by a factor of 30. The signature of the order transition is that if you look at the behavior, this is a dynamical behavior. You can see in one case it collapses very quickly, and in the other, as we increase the interactions, the signal remains more stable. So what we did is that we cut at this 8 microsecond time, and then you can see, I only show few measurements here, so few lines here, but these are all the experimental points, and you can see that there is a change in behavior of this. It's a dynamical phase transition. It's a dynamic. Well, in the theory, it's very abrupt. Here, it doesn't look abrupt because we're including other type of decoherence. But in the theory, it's very sharp. So yes, so here it's a little bit smoothed out because you see we have single particle spontaneous emission and other things. But even with them, we can see a little bit of change in behavior. On the BCS Hamiltonian, this BCS everything is mean field. Yes, this is very mean field. I mean, just doing that dynamics, we're including a little bit of the spontaneous emission, a little bit of the motion of the atoms to account for the broadening that we have. So we can see also the transition between phase 2 and phase 3. In the sense, phase 3 has to have persistent oscillations of the order parameter that we do see. We can see as if going to, by changing this delta S, we can go to this phase. And on the very simple block sphere picture, you can see that it corresponds to two large spins that are locked together and start to oscillate and interfere with each other. So this is kind of phase 3, and we can see some interesting behavior that, well, of course, it's not perfect, but it's something that can that have some access to these different phases. I will explain later, we are trying to move toward P plus IP and D plus ID, because at some point, this is the very simple S-wave behavior, but we can do more in the next experiment. So now let me try to go quickly to the fast generation of entanglement. When people talk about entanglement generation that is used for metrology, people generally, or one of the iconic models is what is called one-axis twisting model. That is a very simple collective Ising model. And the way that this can generate a squeezing is because you can see that at the mean field, this is just a magnetic field that depends on collective magnetization. So if you look at the precession of a distribution, noise distribution, the parts that are closer to the poles are going to precess faster, and the others close to this equator not sharing the initial distribution of a coherent state. And this and the squeezing is characterized by the narrow variance compared to the length of the normalized by the length of the block vector. And this Hamiltonian has been predicted to give a spin squeezing that is scales like n to the 2/3, so not necessarily the Heisenberg scaling, but still good enough. And there has been a lot of experiments trying to reach entanglement generation in this way. So this is nice, of course, but one point to notice is that the entanglement is generated here very close to a stable point. So the dynamics is a little bit slow. Alternative, there was another model that was predicted by Kitawa and Ueda when they wrote this first paper that is called two-axis twisting model, where the dynamics instead is generated very close to a saddle point, and therefore the entanglement grows exponentially fast and can reach even the 1/n scale. So we were able to actually generate this two-axis twisting in the cavity. I'm going to explain briefly how, and actually similar experiments were done in molecules as well, following kind of the similar recipe. So now, instead of having an optical transition, we're going to try to use the optical state as an intermediator. So we eliminate the excited state, but still there could be cavity-mediated interactions through this excited state in the two hyperfine levels. This is an experiment done in rubidium. So we have the atomic transition, omega A, we have the cavity frequency, and we drive the cavity because we need to generate somehow photons. So the idea is that in this case, we can also engineer an exchange Hamiltonian, but in this case, the exchange is generated by I absorb a photon from the probe, emit a cavity photon, this is my red atom, and another blue atom that is in the excited state can absorb this cavity photon and be mapped into the drive, and therefore you can see that we can generate these exchange interactions. But interestingly, we cannot not necessarily only generate these exchange interactions, but if we add another tone, we are able to generate what is called pair racing or lower interactions. That means if I have an atom two atoms in the ground state, if I am going to space two probes at an energy omega c, that is the energy spacing required to flip these two atoms from the ground to the excited state. In that case, an atom can absorb a photon from the probe, emit a photon to the cavity. The photon is absorbed by the other atoms, and the other probe catches back, and then generates these two processes, that is S plus S squared. So with this, we can generate a process that we call pair production process, pair generation process. And the idea is that we can combine both and therefore generate arbitrary SYC models. So basically, when we do these two, we can generate, notice that here this process is S squared minus SC squared. Of course, we are still in the collective manifold, but we can generate couplings that are with arbitrary XX, SY, and SC squared process. In order to probe the dynamics still mean field, what we did is just some type of linear response and try to look at the flow lines of the system. So basically, we prepare the system in the block sphere along one specific initial condition. Then we evolve this Hamiltonian for some time delta the system under some time delta t, and then we look at the difference between the initial state and the final state, and you can see that the difference is proportional to the Hamiltonian. So that way allows us to understand what is the dynamics of the Hamiltonian. And we can see, for example, distinguish the flow lines between stable points or saddle points where the dynamics is going to be unstable along certain direction. So what we did is that by changing the strength of the pumps that we add, we can go back to the one-axis twisting, that we have stable circles. We go back to the other extreme when you have one-axis twisting along the x direction, but in the middle, we can generate a Hamiltonian that is in the form x squared minus sc squared. That is exactly the two-axis twisting Hamiltonian, and these are experimental data. You can probe the flow lines, and you can see the saddle points where the dynamics exponentially grow along one direction and is attractive at the other. So we were able to probe all these two-axis twisting still at the mean field, but see the exponential growth of the dynamics. And finally, very, very quickly, I wanted to tell you a little bit about going beyond two-body interactions. So we know that even though in nature, all the interactions tend to be two-body, because Coulomb interactions is between two particles, one of the ideal situation is we can generate cases where all the particles, multiple particles are interacting with each other at the same time. And well, these are going to be very interesting in the context of error corrections. There are now new gates in ions that they are trying to use these interactions to speed up the generation of entanglement. For quantum simulation in qual-atoms, they were trying to engineer these multi-body interactions by looking at atoms in the lowest band, by looking at effective virtual processes to higher bands. So, but typically what happens is that as you go to higher and higher order of the interactions, they become weaker and weaker, and therefore they are not necessarily ideal because they are so slow that you cannot take advantage of them. So what we did in the cavity is to now introduce two pumps, but now separated by 3 times the energy spacing of the atoms, omega c. So you can see these are separated by omega c. And basically, the idea of the process is that you have one atom absorb from the phone, emit, absorb, emit. These are the 3-body process that happens when you engineer the pumps at a specific separation. And interestingly, because the emitted photon, that is the frequency difference between the pump minus omega c, associated with these two pumps are in opposite directions, the 2-body interactions completely cancel. So that means that the only interactions that we have to leading order are 3-body. Moreover, because we have something that is important is because we have collective interactions. Even though chi3 is small, you are multiplying chi-t by n cubed. So you balance the slower times, and we can see them in the experiment. And we can do not only 3-body, but if you separate the pumps by 4, we have been able to see the 4-body interactions as well. This is where we stop. And we have seen this type of levels. And I think how much time? I'm almost done with time, yes? Okay, perfect. So what is the elephant in the room is that I have ignored completely the dissipation. So at the moment, I have only told you about elastic interactions, but in the cavity, there is dissipation. And this is where the cooperativity comes into play. Because of course the photons are leaking out of the cavity, and what is important is the competition between the elastic interaction and the inelastic. That is the ratio between the cavity detuning and the cavity loss. The point is that if I wanted to make the elastic interaction dominant, then what I will do is to make the detuning larger and larger. That's okay, but what is the cost? If you make the detuning larger and larger, then these terms, chi and gamma, they become slower and slower because the tuning comes in the denominator. And if you make this much slower, then the problem is that a single particle spontaneous emission starts to play a role. So that's where the concept of cooperativity is very important, because the cooperativity is the ratio between the coupling and the two bad scales, the single particle spontaneous emission and the collective dissipation. So in these systems, the key parameter is the cooperativity times n, that is the collective cooperativity. And we are doing also, nevertheless now, experiments where we have delta C equal to 0, no elastic interactions, and wanted to understand in what sense we can suppress the dissipation. and we make the system completely immune to this collective dissipation that happens in the system. And this goes into the lines of subradiance that we know that if you have destructive interference between emitters, you can in fact generate states that are not only subradiant, that is emit light at a slow rate, but also dark, that is just shut down completely the emission. No decay. And there has been a lot of effort, a lot of progress in trying to generate these subradiant states in free space. But the issue is that in free space, in order to do that, you have to put your particles very close to each other, and it's not so easy. So what is our idea? Is trying to use the multi-level structure of the atoms, trying to generate additional interference path to suppress the dissipation. And I don't have time to tell you, but in fact, we found out that by looking at multi-level atoms in the cavity, you can access easily regime where the dissipation is shut down. So this is basically the big picture. If you have a two-level system, you have the atoms, you illuminate the cavity, put all the atoms in the excited state, they emit light, and if they're in the collective, in the fully symmetric regime, the only way out is that they're going to emit all and go back to the ground state. There is another not alternative path. But if you have multi-level atoms, you excite them, and then as a function of time, you always can find states, cases where they are stuck in the excited state because of the destructive interference. And interestingly, not only these states are dark, they remain without decay, but they are entangled. We can show that it's entangled. So there is a way that we can harness all this complicated structure of multi-level atoms for something good. So yes, unfortunately, I don't have more time to tell you about, but I'm here to discuss more. So I told you about the challenge of trying to reach a colder temperature with synthetic degrees of freedom. That is not real, the synthetic degrees of freedom. I told you the story about the S wave, but now we have in the lab implementing P plus IP and D plus ID that has not been seen in my understanding in materials. For the challenge of entanglement generation, I told you how you generate two-axis counter twisting, but still is at an infinite level. So we are trying to see how much its experiments can be pushed to really reach regimes where we can reach entanglement. In the context of beyond two body, actually everything that I show you today, again, also is mean field. We have not seen beyond mean field, but theoretical calculations predict that three-body interactions can generate cat state as the fastest rate that we have seen. So it could be useful for meteorological purposes. In the multi-level dark scale, I only show you that we can create the states that by nature are squeezed, but we can make the squeezing even much larger and scaling with n by harnessing the multi-level structure. And finally, in the case of dissipation at measurements, I didn't tell you anything about that, but what we have seen is that we can generate entanglement via dissipation by just compensating superradiance by a collective drive. And there is this paper where we can see that even we can do, if you keep measuring the system continuously, you should be able to generate this type of entanglement generated transitions that have been studied in other systems, but more easier in this case because the interactions are longer range. And with that, thank you for your attention.